the plan for the last four lectures is today complete the classical treatment. In this case, consider some multi-particle stuff. That is, collisions involve two particles. We sort of started this course with the superballs, but not in 3 dimensions, and there's some other things that we cover between now and then. That was these two force laws, Coulomb and oscillator. And we'll see the very different ways to treat that and some novel ways to treat that. And then we're going to think about taking quite a number of molecules, say 6, 8, 60 for buckyball, or 3 for water, and analyzing the angular momentum properties. And this is something that can immediately lead to quantum mechanical results using a funny surface that we invented. And we'll talk about the surfaces that existed before that, which are mainly done by Russians and French. So, I would first of all do something that's really sophomore physics, but we're going to add a little bit to it just to make it a little more interesting. And we've got lots of demonstrations and simulations that I think are a lot of fun today, and they're being tracked on the second pages of these notes here. And now it takes 2 pages. I think we'll be able to finish in the last 3 lectures will be the ones where we make a connection between classical relativity and quantum. And I think you're going to enjoy that. That's going to be a lot easier than what we've been doing. As a matter of fact, it makes classical mechanics easier. So anyway, we're starting off here with 2 particles, and we're doing the thing that you do right away in sophomore physics, and that's to locate the center of mass. And this is kind of what we did when we developed the collision theory for the superballs. We did the mass-weighted average, and that gave us an important point to begin the whole course. The relative coordinate, in this case we're talking about big fat vectors, vectors that are here 3-dimensional, and the, as I say, the mass-weighted average that gives you a point in 3 space now with a little engineering symbol for center of gravity, center of mass, and the 2 coordinates that involve here are the distance between the 2 and then the coordinate of the center of mass. These are 3-dimensional vector coordinates. And then the other way that you start with are just the 3-dimensional vectors that indicate each of the particles. So the inverse of this transformation between the difference R, the average R, and the R1 and R2 is right here. So this will be at the bottom of the slide as we go through the various algebraic manipulations that are needed to talk about this. So what I like to say is there are 2 views of how things like this happen. One of them is like what Ptolemy, and that's the ancient astronomer that centered all of his views on the Earth, and the Copernican, that's the second one that we'll talk about, but it isn't something that Copernicus did, at least any that I can find in the literature. But let's just start off with the usual view of this type of analysis, in this case just 2 masses, and note that the force, whatever it is, and the idea is that we will be talking about some isotropic force, and you know what those 2 are that we're going to work with, Coulomb and the harmonic oscillator. But it's 3-dimensional Coulomb and 3-dimensional harmonic oscillator now. So the basic idea of conservation momentum, or you could call it Newton 3, the basic thing that leads to is the idea that the action-reaction cancellation occurs perfectly. If we add the MA of those two, we will get to exactly 0. And that is the beginning of the symmetry analysis that we've done now for two particles in a line. We're doing this roughly the same thing for two particles in 3 dimensions. And that idea is very key to this derivation we're doing here first. So after we get done doing this derivation, the thing that I want to turn to is the alternative view. And I use Copernicus' name because he's the one that really told the whole world that we weren't the center of the universe. And that those things out there, including the sun and the moon, particularly the sun and the rest of the stellar heavens, weren't just dancing to our tune at all. And that was a big step for humans to realize they weren't quite as important as they thought they were. Anyway, that view leads to another way to treat this particular problem. And we'll look at both of them simultaneously, more or less, here. So anyway, this is the basic idea of using the difference between, and what I'm talking about here is the force on 1 due to 2. I'm writing that down, and it's saying it's minus the force on 2 due to 1. They're the only actors in town here, and whatever force fields they have, that would be true, regardless of whether the force was isotropic or not. Now, having an isotropic is really obvious that this is true. It's not so obvious when it's not, but nevertheless, that is what we're going to take. These two, this one and the minus version of it, are the ones that determine the equation of motion. And you could feed that into a computer and we'd be done. But I want to go ahead here and do a little bit of the analysis that goes with letting us think about what's happening in a 3-dimensional collision of two objects. So there's this idea of the reduced mass that comes up here. And that kind of comes from these two factors. The basic idea being that this mass 1 times acceleration 1 and mass 2 times acceleration of 2. The difference between those two is given by a difference vector here, associated with something that is a function of what that magnitude actually is. So what I'm doing here is dividing by the distance r1 minus r2, which is what we call r without any subscript. So keep that picture in mind. I'll leave it on that screen there. Most of the discussion of these two particle stuff. So the thing that's important is that this one drops out. Okay, so you're left with this guy minus this guy. So you're ending up here with 2 of those things. Let's get that on the screen right away. And those 2 objects produce, since that annoying 1 and 2 term drops out, leaves us with this interesting combination of mass 1 and mass 2 that is called the reduced mass. Now, it doesn't look reduced, it's got a lot more algebra attached to it. We need to make clear why it's called the reduced mass, but that will come up in the next couple of slides right here. So the basic idea here is that when you look at that factor, you say, oh my gosh, the product over the sum. But what that is the inverse of this thing. I should say the inverse of this is the inverse sum of the masses, the sum of the reciprocals of the mass. So we're going to see this kind of algebra playing out in the discussion of the optics of relativity. So it's worth mentioning
right now I just want to point out to you that if, for example, M1, that's say the big guy, maybe the sun, was much larger than say the little guy, say the Earth, or we can do Earth, Moon, or we can do an astronaut around the Earth, whatever. If M1 is really a lot greater than M2, then I can expand the inverse here. I can expand this expression to give you an approximation. It's just slightly less for M2. M2 here is just a little bit less. It's being multiplied by this factor. And if M2 is really much less than M1, okay, it's vanishingly small. So this thing approaches M2. That's what we're talking about at M2, that's small. If in fact it's the other way around, you still are talking about a reduction. There's a minus sign here. So both of these two extremes, either M2 greater than M1 or M1 greater than M2, both of those extremes have a reduced mass that is a little bit less than the one that's doing the traveling. And so the equation of motion here, reduced mass times acceleration, and I'm talking about acceleration of the vector that's based on whoever, let's say this is the Earth and there's something orbiting it like the Moon, then what I'm talking about, and of course in that case this thing would actually be a little bit inside the Earth there, but I should look that up. I don't actually know where it is. How can it be so stupid? But anyway, certainly if we're talking about the Earth versus the Sun, the center of that would be very close to the center of the Sun, very hot place. But the whole idea is that then we're taking the telemetric view. We're measuring relative to us the motion when we use these equations right here. And that the cost of the price we pay is to have an alterated, a rescaled value for the mass of the object that's actually under motion. Okay, so the other way to do this that I find particularly useful if you're going to be doing geometrical constructions of collisions, and that's what we'll be doing shortly here. This lets us do that fairly easily. This does not. So, and we'll see some funny things that have to do with either one of them as far as the physics goes. But the basic idea here is we're going to work with R1 and R2 as the variables of interest. We're going to be really letting the center, the one with the engineering symbol on it, because of its having no acceleration at all, be the main thing that we refer to. So we're looking at the distance to that from mass 1 and the distance to that from mass 2. And these are the equations that we will use just to rescale the force constant, for example. So what we're going to do is have a reduced force field, or actually sometimes increased, but the basic idea is to put I should say the ratios associated with the two masses onto the coupling constants in a funny kind of way. Well, the price you pay depends on the force field's actual function, whatever it is. If it's Coulomb, it's one thing, oscillator another. It's fourth power, well, you got to do that then. So this is what it looks like for the Coulomb. You, instead of using the good old coupling constant G, big M times little m, we're going to be using the reduced mass squared over the m1 squared for that coupling constant number 1. And then we're going to do a similar thing with coupling constant number 2. So one of the objects will have a larger coupling constant than the other. That's in the case of the Coulomb. Now, the other one we're going to do today is the oscillator, a harmonic oscillator. It's in the green box here. That one is going to have this adjustment made, very simple adjustment, just simply the ratio of the reduced mass to the mass of the object for which that coupling constant measures. So this doesn't seem like a very smart thing to do because, well, it's, after all, Ptolemy's got is the easy way to look at things, isn't it? Copernicus just comes along with this basic idea that the center is out there in space for, well, for our entire solar system with respect to the galaxy. He didn't know about that yet, but the moon and the sun certainly is a good lesson. Now, one of the reasons for having these force constants be very different is that the form of the orbits for these two extreme cases of high symmetry, potential and force laws are very different. And this is very striking. This is, I think, really important to be aware of. If you're talking about good old Coulomb here, which is the thing we've been discussing the last few days, or the oscillator that we've taken up a lot of time with before that, this is the case for two particles. So it's worthwhile doing simulations, and I hope that we'll try again here, getting the Coulombic one going first instead of second. So what I'll do here is look at it, first of all, in the center momentum frame. The frame that Ptolemy would hold as our as something to look at. So there's the dance that Coulomb orbits would do, and right now we're talking about mass ratio here. Now I forget where we have that.
2 up for mass 2 is 1, and mass 1 is 2.
There we go. Mass 1 right here, and then mass 2 right here. So we're talking about 2 to 1, and I just automatically stop. There's a time limit that you can put on this thing, which is worth doing because we're going to be doing scattering that goes out of the screen. But let's just see if I can. I'm going to try it on the old clunker here. Old clunker means it's about what, 4 years. That's the Mac Air here. I'm going to go ahead and try the oscillator on it. Let's see if anything can come up here. Here we go. All right. Okay, and again, this has a stop on it. Actually, maybe it doesn't. But you can see they're really different. These guys get to be close to each other, like there, whereas those guys, they're about as far apart from each other all the time as they can be. And they're both attractive forces. Okay, that's kind of neat to know.
Pause.
Like, score 1 for the visualization aid. Here, just to keep this down a little bit. Okay, now the other frame that we're leaving out here, and let's do it for the complicated dance of the Coulombic orbit, the lab frame. Okay, well, what's the difference? Difference is that this one has some translation, which will be constant because there's no acceleration for the center of momentum. Okay, so this is going to make a prettier pattern. This one just makes 2 ellipses, but this one would march off the screen very nicely for you. And depending on how close you want to get them or how far you want to get them, that would change the pattern radically. But as far as they're concerned, there's no difference between this and that. And we might as well pause here and go back and pick up the oscillators that, as you can imagine, is just the same thing. Translation added to the thing at the extreme right down there. But let's do a hook orbit in the lab frame. Bye-bye. I happened to give it some lesson. Going to the lower right. But I'll pause that so it doesn't continue. Okay, so that's I think an interesting observation, first of all, but we would like to look at the Coulomb attraction and orbits, the dance, more closely.
Those are
And
similar.
to do that, this way of giving different force constants is really useful. Now let's just think about it for a moment here. At first, you might say, how could that be? Here's this one's got a force constant with respect to the origin there, and the other one's got the other one. Why should those be different? That I claim we proved, but it is necessary, and it just amounts to rescaling the size of the orbit. So the idea is that here I get a complicated, say, Rutherford scattering going here, and that's what I really want to talk about on this ski theme. After I get that set up, I draw the other side very easily just by changing my scale. That's really the motivation for the trick, or the Copernican, as I call it, Copernican trick. Okay, let's go ahead and pause this so it doesn't use our CPU up, because we do have some more complicated things to do here. And particularly on this one's doing pretty well for an old clunk. Now, that means I have to bring it back home here and do the same with this one. And while we're at it as well for this one here. Okay, so let's just quickly go through what goes on here. The orbits are mass-scaled copies. Equal aspect ratio, but eccentricity, orientation, those are all the same. But this, these guys, those are getting scaled, rescaled. And that's really what this boils down to. So the formulas for doing that in the harmonic oscillator case, and what's different is the time scale for orbits. The ratios of these things, that's going to be different if we do these rescalings here for the basic idea, the difference in placement of center for the Coulomb case of foci for the oscillator. That's really what's making this thing. It's kind of weird, okay? But if you do that, then you only have to draw one, you only have to find a construction for one of the orbits, and presumably get all you need in information for the other one, number one versus number two. Now, before I go on, I'm going to show you some more elegant geometry that goes with this. But I have to warn you, you probably already heard this. Bring another body, and this all goes to crap. Three bodies just has no analytic solutions. All kinds of nice approximations, like finding Lagrangian points for a small body, like a satellite, like our infrared telescope, the Webb, that's going to be going there. We hope it makes it. That's going to be spectacular if it does, and we're in deep crap if it doesn't. So it's really a gamble, but it is a gamble worth, it's unbelievable what it's worth. I mean, think of how much the Hubble has been to give to culture, right? The Hubble, just a visual, mostly visual optical telescope, right? This thing is going to see things, unbelievable things. So, that said, that's why I like to think of the geometry and make a fuss about it. But there are a couple of things that are more down to earth. This is something, as sophomore physics, every pool sharp knows this. The basic idea is, here's a CM view. Okay, I'm going to be able to do the geometry of that really elegantly. I just do the same geometry that we've already done with the Rutherford scattering, assuming that the nucleus was infinite mass and that the alpha particle didn't make it move as it scattered. Now we're making the 8-ball move or whatever. And the idea here is that in order to get the lab view for this, and this is imagining a very common form of pool hall scattering involving those two objects. They're rolling, admittedly, they're not just flying without rotation. We're going to be talking about rotation soon enough here, but as far as their behavior in the simplest description, it's well known that if you hit the 8-ball that you don't want to sink into a pocket, right? That's the 8-ball game, right? You want to make sure that, I'm sorry, you don't want to sink cue ball, isn't that right? You want to realize that wherever you're sending the 8-ball is going to be at right angles to where you're sending that. That's without any English, right? Without any spin. I'm sort of leaving rotation out of this. But to see that, to convert this arbitrary scattering angle here in the center of momentum, center of mass, gives you this, and all you need to do to get the lab frame, that is, if you transform from C over to lab, you do it by subtracting whatever the center of mass velocity was from all of the velocities you're dealing with, both of the velocities that you're dealing with. So this is familiar to us. So I think I mentioned that very early on, the idea of conservation of momentum and the idea of translation, the idea that if I want to get you guys all moving, you're all sitting right now, I want you to go 3 miles an hour that way, I start walking 3 miles an hour this way, and for me, you're all moving, right? Everything in the whole universe is just moving another 3 miles an hour, according to this guy. Now that's for the next 3 days, that's bogus, completely bogus with respect to light. Light's got its speed, and my moving 300,000 miles per hour affects it not one bit. And we've got to understand why that is. That's one of the things I call a word mystery box. So, just to get off the topic here a little bit, getting you ready for that. Among other things will happen when we go into modern physics. In any case, with this, it's very easy to simply add that, and then notice, and let's just drop back here, not forward but back to this, and I'm going to do it on this one as well. I want you to go ahead and see the simulation of this just for the heck of it. Okay, we'll do it on these two screens right here. Here is the center of momentum simulation for hard collision, hard mass collision in the Super Ball program. Okay, so there's the view, and I've got it set so it stops when it hits the top. So that's the end of that. And then here is the hard collision between those two equal mass balls, and that's what we're talking about here. And there you can see it stops it early, but with a little bit more time here, resume and then pause. It's pretty clear we got a right angle for that. Okay, so the idea of getting a right angle when the two masses are equal is really another example of Thales geometry. And let me get it back again here and point that out. What I'm talking about is that this angle here is subtending a diameter. So no matter where this is, it's always going to be a right angle. So that's one of the first theorems of geometry, 600 BCE, 300 years before Euclid. Okay? All right, let's get this one back home as well. Although I think it's probably worth noting that this one does a hard collision in the lab frame as well. That's what we're interested in here, is the lab frame, very clearly a right angle occurring in that case. Okay, now what we've got to do is make stuff like this happen. We know how to do this with ruler and compass for Rutherford scattering or any sort of Coulomb scattering. We know how to do it for oscillator scattering, but that's another story for another time. Then we go ahead and do the Galilean transformation, and let's get this thing back in operation here. And it didn't seem to go back into operation right away. There we go. Okay, so what I would like to look at is the center of mass, cm, view, and that's just what we already did. We set up a beam asymptote, or I should say a beam direction, and then we set up a impact parameter, which is the minor radius of the hyperbola that we're going to be making here. And we're assuming repulsive things, so we'll get nothing but hyperbolas. But if it was attractive, or if it was low energy attractive, we'd still be playing with something like that to give the initial conditions of one mass, say the alpha particle, and then here's the gold nucleus that we were shooting in the last lecture, and we're imagining that it's not as heavy as that. Now we have to take its motion into account, so we're just saying this one's maybe twice as heavy as this, or even this is lighter than that, whatever. Whatever that mass ratio is, we've got a balance around here, so we've got to make the proportion between this particular semi-minor radius exactly to this one be exactly the mass ratio inverted. So we draw this first, and then very quickly with ruler and compass we can draw that. The scattering angles, all of that are reproduced down here from up here. Okay, so this is the case where we're talking 2-to-1 mass ratio, all right? And then what we're going to do is we're going to do whatever velocity subtraction we want to do to make the number 2 mass stand still initially. So I'm just going to come over here and put my marker for the new velocities. That is, I'm going to subtract this velocity from everybody, and that's going to give me this vector here and this vector here, just like the pull shot. All right? So that kind of tells you that gives you the angles in the laboratory number 1 and number 2. That it certainly does. But the actual trajectories and all of that, what's going on there? That's what we need to talk about. Now, I'll go ahead and simulate this just real quickly. This is a Coulomb collision in the CM frame. We'll look at that first. And off it goes. They repel each other and lead forever on lines that are very clearly drawn by a geometrical construction such as that one. Now, you might say, oh, this is trivial for the lab frame I just added. Don't I just add velocity to everything here? Well, not quite. That's not going to get you what really happens. So let me bring this one back and go ahead and do the view of this thing using lab frame as a reference point. Okay, that's what I'm trying to picture in this frame right here. Okay. The idea that there is a point where this thing started, and this thing was way off here. Now, that's the catch, you see, is how far off do I have to get so that this long-range force called a Coulomb isn't disturbing it, isn't making it move. That turns out to be a real stickler. Okay, I just say, well, it was there and I came in and it left there, right? That's wrong. That's what I want to show you in the details. This is what really bugged me, because I'd already discovered how to do these complicated calculations by ruler and compass, and I was figuring, yeah, I should be able to do a lab frame too. Turns out lab frame doesn't exist. That's the way a mathematician would say it. So anyway, this is out of a paper that was part of a student project at Georgia Tech. There were 4 students that participated in various parts of this. This is just one of the parts. Anyway, there's the diagram that you can do so easily, so elegantly, just dealing with the velocity changes. This is an attempt to show what it looks like in the lab frame. Call it the slab frame. It's not there. This story I want to make as clear as I can. Given this, then what? Okay, and you see the trouble with it is the Coulomb field has to do this interval. That's what's going to screw everything. This is where that 1 over z, right, that one integral of a power law that gives you all of the beauty of complex variables and the power of it, here it trashes our lab frame. Okay. So what's going on here? And this is just, I'll just read this caption pointing at what's going on here. This lab picture of this CM deal, but then the lab velocities are shown as though we really knew where they were exactly. Okay, this begins with both particles. Both these are particles going to repel each other, but I need to put them at infinity to start with. Okay, one of the particles is at rest. The lighter one is even further away, say about 3 miles away, okay? And the lighter particle is moving toward, I've got to go down this, sprint down to Fort Smith, okay, at least, okay, and put my so-called resting particle, the target, okay, there, and then I've got to go to Louisiana and shoot the thing that's going to hit it, okay? On this scale. So we're talking about exponential time before the collision occurs. That's really the rub here that makes this thing crazy. Okay, so let's fast forward ahead. When the heavy particle first appears in this picture, and this is 1 or 2 years before the actual collision is going to happen. But anyway, it's come all the way up from Fort Smith. And it's sitting here, you know, and then in another 10⁶ seconds, a fraction of a year, it's here, a month or so. But it's picking up speed, you see, but it's really just creeping, okay? It's going to be a couple of years before we get this guy to show up here and actually push on this thing. Okay? The heavier particle continues creeping until finally the lighter particle arrives into this picture and moves through in about 12 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this thing scatters and reaches pretty near its final velocity. So that's the story you really need to tell about Coulomb scattering in a lab frame. The lab frame doesn't exist. It's only an approximation. And this is just with, there are only 2 particles in the whole universe. If there's others, you've got worried about them too, at a logarithmic level. Okay, so that I thought was quite amusing. And you can imagine the American Journal of Physics, I said, wait a minute, we never heard this story. And after a while, I go, yeah, yeah, that's a good lesson about the what it means to be a force with long range, which is cool. Okay. We had already mentioned that. Okay, so here's the other thing that happens, and this is pretty scary. Where are the asymptotes? I figured out with a ruler and compass I could find where the laboratory asymptotes were. And I figured I could do a retractive. That's even a little bit dicier. But the idea that you have asymptotes, after 100 seconds, it'll have moved. I mean, here's, I'm just drawing lines between them, and those are eventually going to form asymptotes. But the asymptotes creep. Now, as we continue in the so-called lab frame, these guys are going to be moving, and it'll take them, about a year to get out to here. By then, they'll be really close to the angles that we were calculating using our ruler and compass, but they won't be quite there yet. And so this is a logarithm, you can recommend sort of logarithmic graph paper if you draw them at equal time intervals and then scale it. Okay, so that's the other thing that happens with this. And it'll happen with attractive. This time you put them both at infinity, but put that light one further infinity than this one, and it sucks it in. Year here, it's maybe 6 months here. Oh, it's the day before the collision right here, and then, va-boom! It gets jerked through in a few seconds. That's the time scale for Coulomb operations, if you're really doing it precisely. I mean, for some people, this is almost enough to make them give up physics. I hope there's nobody in here that's scared that much by this, but you should be aware of it. It's one of many, I think, interesting effects that exist for us to contemplate. Okay, the next stuff that we're going to be doing here is a completely different topic, because now the particles that we're playing with are going to be glued together more or less rigidly. And I say less rigidly because molecules are not completely rigid. They can't be. They're basically Coulomb-like forces holding them together and making very strange force laws. So this is where we begin to do the sophomore physics that's associated with angular momentum and rotation. So at this point, we make really the first equation that we've already talked a little bit about, but it was just R times P. Now we got R cross P. We mentioned that a little bit briefly. But here's where we're going to be building quadratic forms that are generalizations of the quadratic forms we did on the first or second day of lectures when we had just superballs going back and forth on a line. Now we're going to be talking about the angular momentum and angular velocity of, well, any number of particles held more or less rigidly, and I'm going to start with them being exactly rigid. And just exactly enough so that the forces that they have between them are perfect minuses of each other. And any applied force that you might do could be different, a force on each of the three masses, but these are going to resist it, and assuming that these forces were just a few pixels and these are very enormous, there isn't going to be much change of shape of this thing. If it is, that it will be going into a vibrational mode of depending on symmetry and all sorts of things that we talk about in the group theory course that comes next. Anyway, the basic idea of a derivative of the a derivative of the angular momentum being the r cross the force, that is, the derivative of the momentum is the torque. That's what we are setting up there. And all of this is something that's very often completely left out of UP courses. It's the end, and there was various things that delayed things, so never get this. So this, I've taken a lot more space in the textbook to write all of this down. But the basic idea is that it could be much worse than what is going to happen here. I could be looking at cross products for every single one of the forces in there. It turns out that I can get away from that fairly easily. It turns out they look like a big nuisance, but when you write them out explicitly and carefully, you can see the connecting masses are causing us to not have to worry about very much stuff. I'm going to keep that screen down there going as well. So anyway, that's what we're headed to here, is to get the equivalent of the F equal ma, but really the momentum dot, momentum time derivative equal to some kind of generalized force. In this case, the generalized force is called a torque. So just getting used to this is really all I want to talk about today. The algebra you can go through yourself, the review of sophomore physics. But basically, this is the equation I'd like to have a look at in some detail and look at some interesting things that it does. Get some feeling for rigid body mechanics that happens. So this is the analogy of this. This is the three-dimensional linear momentum. This is the three-dimensional angular momentum. This one is just a force you're used to. This one is a r-cross force you're used to, but for each particle summed up. And that has three dimensions to do a sum over. I'm not using dummy index rule right there. Okay, so the question is, what's the geometry of this? How can we you know, get this so that we can put it in a visual part of our brain? The algebra is all wonderful, and certainly if we're going to do a computer program, we've got to have this. But what I'd like to do is go a little further than that. So the thing that I want to answer at this point, and I've got a marvelous little song that maybe you've heard, but if you haven't, I've got TC has located a website that lets you see a whole bunch of versions of that song. It may be one of the most popular songs that has ever been written. This is went. I think it came out in the 50s, if that's right, and it's really cool. Anyway, here's the other reason that I'm bringing this up, and I seem to have left this object somewhere else. I usually keep it back there in the thing, and I thought it maybe that I took it home, and that's a good way to lose something. Anyway, I built an aluminum boomerang in 1965 or so. Now, most of the boomerangs are in Australia are made out of some exotic pieces of wood that are really quite light, but some of them are heavier and strong. This is strong and not so light. But in any case, the basic idea of this is the effect of the torque. And where's the torque coming from? Well, this is where you have to keep using your right hand to figure out what's going on. First of all, if the boomerang has been thrown so that it is flying into the board here, and has a right-hand rule angular momentum, the thumb being the L vector, then there will be higher lift on the upper part of the boomerang's wing that has the velocity plus the rotation, and there'll be maybe even no lift on this one because it might be that the wing is just coming back with exactly the speed that the boomerang is a linear velocity. Anyway, it's going to be less than this. in the normal situation. So that makes, you put your hand on the force, the fingers on the direction of the force, and the thumb points in the direction of the angular momentum. So that means that this angular momentum is going to grab onto, this torque, N, is going to grab onto the angular momentum and pull it around. Okay? Now, I really think I should have probably gone to that example right there first, but I figured we'd do this just to, just to give something that really is a spectacular result of that N equal the torque equal the derivative of the angular momentum. So that's the equation we're solving here. Okay, so what happens is that if the boomerang is thrown with enough angle so that it has a little bit of lift to keep it more or less level with the ground, that it will go all the way around a circle. And the ideal, neglecting other effects, would be that it would come back directly after completing a perfect circle. Well, it kind of does that, but it does it in a funny kind of way, and that's what's being shown on these other slides here, and what the song is all about. And that is, how do you get a boomerang to come back? And the Aborigine that's singing the song is complaining about the fact that he can't get his boomerang to come back. So we'll take a look at that, or take a listen to that in just a minute. But here's the thing that happens is that as this wing cuts through, it leaves, it's getting lift, so that means air molecules are being pushed down by the aerodynamic wing, and the bad air that as a result of that is felt by both wings as they swing into the bad air. And so that's another torque. That's a torque that tends to lift the thing. That's this torque right here. And that is a much smaller torque, but while this thing is going around, it's being brought into a horizontal position. So by the time it gets over here, if everything's working perfectly, you can have the thing literally come up to a fairly high altitude and come to a stop. The linear velocity can be very close to zero. That is, it would then settle down. And if you are pretty brave, you actually could catch it, but I wouldn't try it with this particular one. In any case, that was the thing that allowed me to throw a hunk of aluminum into the air and have it be there for 18 seconds. Easily get 15 seconds, but if you worked a little bit harder, you get 18. And somebody that really knew how to throw these things could probably get 20. So that's a piece of aluminum. Okay, with the wooden ones, you can get a lot more than that. Okay. Now, one of the things that's true is if you figure, well, if two wings is good, maybe 3 is better. Well, 3 is going to give you really a lot of bad air. It's going to make this torque really low. So the thing is going to start out like this, and it's going to level and turn over, and then it'll go the other way. Okay, so you'll get figure 8 things, and then it could just do loopy-loops, all kinds of crazy things. Boomerangs with 3 wings, you don't see them in Australia, but you do see them as toys sometimes, and they're quite exotic. They go all over them in very interesting patterns. In any case, I think we have a little bit of time, so if you don't mind, I think this one has a speaker that you can hear. I probably ought to make sure that that is turned on, so I'll back off here. I actually intended to make this thing I'm trying to get to. There should be a sound adjustment here, and I don't see it. I will attempt to use this one right here, see if it will give us enough amplitude to reach there. And then let's go ahead and I will simply click on this thing, and go to the page and see if we can get this to come up. Okay, and this is the guy we want to play. Now, lots of versions of this. So we got to get rid of the ad. But here he is. So. Can you hear that?
In the backlands of Australia, many years ago, the Aborigine tribes were meeting, having a big powwow.
We got a lot of trouble, Chief, on account of your son Mac.
My boy Mac, why? What's wrong with him?
Our boomerang won't come back.
Your boomerang won't come back.
My boomerang won't come back. My boomerang won't come back. I've waved the thing all over the place. Practiced till I was black in the face. I'm a big disgrace, the Aborigine race. My boomerang won't come back. I can ride a kangaroo. Make kickajou stew. But I'm a big disgrace, the Aborigine race. My boomerang won't come back. Banished him from the tribe then and sent him on his way. He had a backless boomerang, so here he could not sing.
Ostracized him.
This is nice, isn't it? Getting banished at my time of life. What a way to spend an evening. Sitting on a rock in the middle of the desert with my boomerang in my hand. I should very likely get bushwhacked. Get out of it!
Bushwhacked, right.
Bushwhacking animal. Think I'll make a nice cup of tea. Good gracious. There goes a kangaroo. Let me have a practice with my boomerang. Get him right behind the left ear. Now then, slowly back.
If you throw that thing at me, I'll jump right on your head.
Isn't it marvellous? Got a land full of kangaroos and I like to pick that one.
For 3 long months he sat there, or maybe it was 4. Then an old man in a kangaroo skin came knocking at his door.
I'm the local witch doctor, son. They call me George Elfie Black. Now tell me, what's your trouble, boy?
My boomerang won't come back.
Your boomerang won't come back?
My boomerang won't come back. My boomerang won't come back. I'll wave the thing all over the place. Practiced till I was black in the face. I'm a big disgrace, the Aborigine race. My boomerang won't come back.
Don't worry, boy, I know the trick, and to you I'm gonna show it. If you want your boomerang to come back, well, first you've got to throw it.
Oh yes, never thought of that.
Daddy will be pleased. Must have a go.
Excuse me.
Now then, slowly back and throw.
There's the sound of thanks. Got an earphone.
Oh my God. I'm a flying doctor.
Can you do first aid?
Don't talk to me about first aid, boy. You owe me 14 chickens, you know. Learn to throw the boomerang, you know. First thing first.
Yes, I know that, but I mean, I think on this occasion, you know.
Anyway, felt it be amusing. It's interesting to see how this thing evolved over the years. TC's managed to collect an entire.
That's a pre-existing playlist, Bill.
Yeah.
The one we had linked got copyright
Copyright.
infringement,
Yeah,
so
but,
they won't let us
all the
link
rest
to
of
it
them
anymore.
are so.
This
Okay.
one seemed worse.
All right,
More-
back to physics. Where you can feel it without getting hurt by being hit by a boomerang is with this little gadget right here. And this gives you a little bit of a feeling for how a gyro compass works. So we're going to do the dynamics of the Euler angle machine. Forget the group operator for a while. We'll just spin this guy. It's good bearing, so he holds the spin pretty well. And the idea then will be, and that's the thing maybe I should have shown first before I show the boomerang, because it's more complicated. But the Z rotation in the alpha dial is what's making this thing have an angular momentum when I spin it up. And if I use a right hand rule so that the angular momentum is pointing up right here, then turning the thing this way, that is applying a torque that is also this way, okay, just helps the thing stay up. Okay, so once again, I'm going to spin it with an angular momentum up, and then I'm going to do this, and it rights it. It was trying to turn over there a little bit, just because it's a little off balance, but the basic idea was that it would right itself. Now this time, I go the same way with angular momentum. L is up in the room, and I'm going to go the other way. You see what happens is it turns completely over. In fact, it would keep going, and then spring back. Try to get into this position. With me, if I'm going to rotate the frame on the thing, it wants to get with me. That's really what it boils down to. That's a quantum mechanical effect right there. It's trying to cut down on the difference in phase velocity, and it's doing it classically. So that's the basic idea of this. And let me go ahead and bring this one back online as well. And to do that, I have to play it to make it convenient. But basic idea is, if it's lined up like we had it, it would stay that way if I made the frame that held it go in the same direction. Now, I point out here, this is the gyrocompass idea, a very high-speed ball in a vacuum container, so it could turn without slowing down, would similarly seek the axis of the Earth. And that's all there is to a gyrocompass. They're very expensive because you have to get a very high speed because the Earth is going so darn slowly. But it's amazing. This little ball can feel, if it's built sort of like that with a gimbal mount, can feel the slow rotation of the Earth and literally swing around. Well, of course, what happens is it goes past it because it has inertia. And, oh, wait a minute, I got to go back again. That's called hunting. So the gyrocompass has to have a little damping mechanism to get it to settle down in wherever the Earth's axis is, and that then tells you true north. And for a long time, that was the only way we could find true north. Now we've got GPS, all that kind of stuff, right? Ring gyros, we have optical gyros now. That's completely make this mechanics obsolete. But it's still a very beautiful sort of thing that is going on, and it is the as I pointed out to you, with our two-state systems, the little magnetic ball here lined up with a magnetic field in exactly the way that the rotating ball lines up with a rotational vector field. The analogy is very deep, a very deep thing. So, as I say, this is, I guess, the takeaway message that we're going to poke about as we go into the modern physics of waves doing things with each other. The general rule is gyros tend to line up so they are rotating with whatever is most closely coupled to them. That's the easy way to see which way the gyro is going to go. Other way is to use your right hand and two right hands, right? Torque and angular momentum. But this is what's behind that. Okay, now we've got enough time here, I think, to do one more thing that is really quite, I think, spectacular, and that is the motion of a rigid body that, well, for the first go around here, I'll just imagine that we have a rigid body that's no symmetry to it. It's got a crank shape to it. It's a rod that's been bent off the axis, has its own mass, say that's the only mass, that this is a very light support here. And there's a ball bearing that's, or a air bearing or something that lets this thing rotate without the friction or any other forces than the ones that have to do with inertia. Angular momentum being constant. Now, angular momentum, as we've said, is r cross velocity. But if that velocity already is a cross, then it's time to use the triple or Levi-Civita tensor, but we'll just use the old-fashioned Gibbs way of writing this thing. And the idea is that what comes out of this is the angular momentum is a quadratic form of a inertia tensor. So here's where we get to use the very same geometry we use to make Lagrangian Hamiltonian analogies and quadratic forms. But here we're talking about a 3x3 matrix with plenty of off-diagonal components. We didn't have anything but masses on the diagonal when we did our Hamiltonian Lagrangian case of a tensor. But here, very quickly, you see from this triple cross product that we get a dot product of the first and third times the middle one, and then the first and second times the third. That gives us this expression for a tensor. A unit tensor right here, that's just a scalar product that results from this term here, but this one right here is that's a vector, a tensor, and that is what we're going to call I. That's this thing right here, inertia tensor. So it's really a very simple relationship between the angular momentum, the kind of thing that Hamilton wants to work with, and the angular velocity, the kind of thing that the French mechanics want to work with, velocity, Lagrangian territory. The L here, momentum, that's Hamiltonian territory. So we're going to write this thing both in the way that the French would write it, that's the using angular velocity and inertia tensor, and then what the Russians and the Irish, the Hamilton school uses. Anyway, that's the component form. There's a matrix that it would have. It's just a question of putting in the components for what we have shown here. And the basic idea is that I will be able to calculate, given the omega angular velocity due to the bearing rotating this thing, I need to also calculate the tensor that gives me the angular momentum when I multiply it by the angular velocity. So this guy right here, to get this guy, I need to stuff these components. I'm sorry, I need to stuff these components right here, the actual location of the mass, x, y, and z. We only have two numbers here to stick in, but they have to go in the right places. And that gives me a thing that looks like that. Very simple matrix. That's not diagonal. Okay, so that's what makes this a little bit more complicated and something that you don't usually see in sophomore physics. But you should. I mean, we should have ways of getting to this more quickly. So many things that use tensor relations like this. Virtually every piece of your cell phone and all of those things that we're going to be building in the future involve tensors of some kind in electrodynamic effects. But here it's just simple mechanics. And what it's telling us is that the angular velocity, angular momentum vector is got a minus sign in this direction and a positive sign in this direction, or maybe the other way around. But anyway, it tells us that the L, and you could have guessed that with your right and left hands, somewhere over here, this is what the vector actually is. This thing right here is there, but it's attached to this body, this axial axis plus mass. And so as it rotates, the angular momentum is being forced around like that, and that means there's a horrendous torque being applied to the bearings as this thing rotates. Okay. Now, if it is a perfect bearing, that is no friction, and it's established contact with the whatever it is, say the Earth, this would just go. It doesn't matter how big that force is. This thing will not slow down because of that force. And that's something that's really hard to visualize, and that's what makes the gyrocompass work, actually. As long as those bearings are really perfect, the forces that you normally experience when you pick up a gyroscope, say in a trick suitcase, right? You pick it up and it starts doing this, right? Well, that's just because you don't have your perfect bearing. If you have a perfect bearing, it's stuck. And it will not slow down as a result of that. How do you get these things to go away? Anyway, that is what's at work here. So the bearing torque on this thing is just periodic and constant. There's nothing except friction that would friction, or just simply it breaks loose from the mounts here. So the force could be arbitrarily large. If the bearing can stand it, it will continue rotating. So the basic idea, of course, is that when you make a tensor like this is just writing it all out in a good old-fashioned notation. You make a tensor like that, if you pick the right axis, you can have a tensor like we were used to with our Hamiltonian and Lagrangian relations that's diagonal. And that, of course, is what we're looking for most of the time here. But if you have a body that is now loose from the bearing, and that's what I really want to talk about here. If you have a body that's loose from the bearing, an actual flying body, it's going to have a relationship between the angular velocity and the angular momentum. It's just like the one we've played with in chapter 12 of the introductory unit. This is no longer the Lagrangian, this is no longer the Hamiltonian, but the relationship is the same. There's an ellipsoid that's describing the equation of this quadratic form, and in this particular case it's a particularly simple one because we've found those magic directions in an object. However low symmetry it has, there exists in a rigid body a coordinate system x, y, and z that makes the inertia tensor diagonal. It's your job to find that, but if it has symmetry, you pretty much are sure that the symmetry axes are going to be the things that have the directions of eigenvectors of this matrix. So that's the basic idea. The Hamiltonian form of the equation involves the L ellipsoid. That's this one right here. And it is quite equivalent to the Lagrangian form. So here's Irish versus French again, but now it's talking about how we're going to describe a rigid body and its rotational motion, which could be pretty wobbly, and that's what I want to demonstrate with it. So I say recall these quadratic forms, that geometry that we talked about way back, and this is lecture 8, actually it was before that, in our discussions at the beginning of this course. So that's what we're dealing with here, and here is just a picture of that relationship. The L, basically the gradient of the kinetic energy, which is the quadratic form differentiated with its independent variable. That's the Lagrangian way of going at this thing. And that L is going to be I dot the velocity. And then the flip of that is, Hamilton says, no, you don't do it that way. Turn your thing around so that you use the inverse of that matrix. And the derivative of that with respect to angular momentum will be your angular velocity. Okay. So that's what we're, that's it in a nutshell for rigid bodies. And now the question is, how do they behave, and how do you do the quantum mechanics or something like that? That's one of the things that we can get a quick glimpse of that. But the basic idea is that anything, any object, like a book that you put a rubber band around so it doesn't open, or a tennis racket, if you try to take a tennis racket and make it do a rotation like that, by the time it gets to here, it will have turned. And it will turn over. You can bet people there are ways to make it actually go maybe one rotation, but as you're going to see, this thing right here makes a liar out of you with regard to keeping that rotation going. So here we have an actual a demo that shows that. I'm going to put the all of these equations on the board down there, and then we'll use the other one for various demonstrations of the weirdness of the rotational motion that this thing involves. Okay, I'm going to go ahead and start this one right here, and might as well do the part of the experiment that is real. So it's the air bearing again that we had going before, and then I just take a fairly sharp pencil, and this guy right here is a ball that has a very thick brass rod going through what we could call the x-axis, and then on the y-axis it has just a little 1/8-inch brass rod with a little drill place so I can stick the pencil there, because that's the magic axis, or unmagic thing. And then the other axis right here doesn't have any brass at all, it's just plastic, the same plastic the whole wall's made out of. So that's the rotor that we have, and it's smooth enough that it can turn very nicely in its pocket here. And what I can do is color one side of the y-axis dark, but leave the other side with nothing, right? So if it's going to do something wild like turn over, you'll see it just by the fact that this won't be black on top anymore. So let's see if I can get it going. Now the other side comes up, and finally back again. Okay, so that's what we got to understand. What in the heck is happening that causes this thing with no torque? I'll go ahead and do it here where I can spin it faster. No torque from the outside, and that thing is being flipped completely over. There's a movie called The Day the Earth Turned Over. Anybody see that? You have to stay up pretty late at night to get that one. It's really old, but they had the Earth turn over. They didn't explain this effect, but maybe that could be what goes on. Now, while that's going, it's a magic thing, I'll go ahead and turn on the actual demo here, which you can see a little bit more clearly. And I fumble with this thing a little bit here, trying to get that ballpoint pen to sit in a pocket. But that's what you're looking at right now on the table here. And then on this screen here, what I'd like to do is show you some other things. It always occurred to me that this should really be done as somebody has some extra time on the space lab, on the or on the shuttles that go between there. I'm going to cancel this thing out right for now. But this one right here is happened accidentally. It's only recently that they showed this one. How's that thing doing? It's starting to slow down. A little bit of friction. Anyway, it's still doing this crazy thing. So here is this. This was discovered quite accidentally when somebody unscrewed one of the VCN connectors.
live on YouTube TV.
There we go. He just unscrewed the thing, and look what it did. Exactly the thing that we're talking about. Except it's a little more rapid in its turnaround. Just gave a little bit of a kick and got off of what we call the separatrix. And there they don't have any of the burbling air that causes this thing to change. You can see now that it isn't getting on the axis very much. But this one, perfectly periodic. Cancel this one. Okay, so those are a couple of demos of things that happen in this rotational weirdness. I'm going to get this one over here as well. And then just to not have a fire in this room, I'm going to turn this off because there's a motor in there and it gets pretty hot. So anyway, this one right here, and you could go ahead and look at this one on here. This is one you usually do. Just take a book and put some rubber bands around it. They don't show that. Maybe it's a book that's very tight. And just try to throw the book so that it does that. It won't do it. And that's a good way to demonstrate. But this is amazing. This is when the Van Allen belt was discovered. But it almost didn't happen because they got smarter than they thought they were. Now this is from a book that I've already shown you by Rick Heller. You can read the comments of these people and you can see that they are not understanding what's going on there. And that's pretty much a characteristic. This is the paper about it that we wrote a long time ago. But this NASA, as Rick calls it, early blunder. Okay. And by the way, this book is now available, and I will use it for the course, part of the course coming up in the spring. Semi-classical way is the name of it. I've got the bookstore buying the book, but you can find it online at a pretty low price. It's actually getting to be quite popular. But anyway, what happened was that they figured what a good way to to make a satellite that would always point when it came around at the Earth. And that was the idea. And there would be antennas that swung out from it. But the trouble is that this is the high energy state of that quadratic form. So as the time went on, it started doing this because there was energy lost. And this is the energy surface I like to draw because it's, useful for all kinds of things. But the idea is that as it started to wobble a little bit, it started losing energy faster. So basically, it started out on the high energy side of the what I call rotational energy surface. That's our discovery. It didn't take much to make a discovery in this field. It's so abstruse. But the idea is that Rick has just sketched sort of a trajectory on there that goes across the separatrix and it settles in the valley. So it's basically energy loss due to internal frictions. And when it's in this state, then it's doing this. It's tumbling end over end, which should have been a complete disaster. It should have fallen apart. But it didn't because the antennas still were flopping. All they had to do is make a modulator that would read the signal just as the antenna was in a certain orientation as it passed over. And we got to see the Van Allen belt for the first time. That's part of our history in astrophysics, geophysics. So I hold that up to you as an example of weird things that happen with rotations. So I'm going to end here, but there's a lot more to this, and these are things that we've covered in the parts of the course that's coming up. This is what we call a rotational energy surface. This is what's called a constant energy surface. That's what the Russians used. Then there's an angular velocity surface that isn't good for much of anything, so the French lose on this one completely. These are intersection of these two, but this is the one where you plot the energy of the thing as a function of the direction of the angular momentum for fixed magnitude. And that lets you use this thing for quantum mechanics. These are the very precise eigenvalues of the energy. The energy is being measured from the center here. Lowest state, highest state for a prolate molecule. The novelate molecule has the shape of a frisbee. That's this one right here. And then water molecules somewhere in between there. That's water molecules behavior. And it's an asymmetric rotor, just like that device, that satellite that went crazy. And this is where the water molecule also goes crazy. And I used to have a water molecule here I could show you. But I think we'll, since we're already over time, we'll quit right here. Okay.